Okay, good afternoon, class. Welcome to week 3 of the metallographic preparation course. We are now getting into the subject of mounting techniques. So to kind of give an overview, we're going to look at the purpose of mounting, the size of some of the samples, types of mounting techniques, and then sample orientation. The purpose of why we mount samples, the biggest one is going to be the making it convenient for you to handle the specimens. Not every sample is going to be easy to work with, so it really helps because you might have an irregular shaped or just an awkward geometry, fragile samples, maybe even super small in size that you cannot just with your bare fingers hold on to. So it makes it very convenient to be able to proceed through these metallographic steps without taking your fingers off. The next big thing would be to protect those samples, especially the edges, if you're going to be doing any type of surface or edge analysis. The examination of platings, coatings, and other surface treatments such as carburizing, nitriding. You might have an oxidation layer you want to look at. So without the aid of mounting that sample, then the abrasive pads, the way they work is it's going to wear out that outer surface first, rounding it off. And so the higher the magnification you analyze your sample, especially around the edges, it'll look very rounded. And so if you're looking at coatings that are supposed to have a minimum thickness requirement, this would be a very poor way of looking at that surface because that edge being round, most definitely you're going to have a much thinner measurement of that coating or plating than you would have by mounting it. Also a nice thing is the fact that you can prepare multiple samples at once, especially, and I mean, just rule of thumb, if you're going to mount more than one sample together in one mount, then it's going to be best if they were of similar material. Say, for instance, all of it be 6061 aluminum. One can be annealed, one can be hardened. That's fine. It's still the same material versus one copper and one tool steel. You're not going to put both of those together in the same mount because of the hardness difference, and you'll also see that the copper will never polish out nicely. So multiple samples can be prepared at once, so it does save on time and consumables, which are the biggest uses when it comes to materials in the lab. And another bonus is that you have the ability to label and identify those samples without damaging your specimen. So after you mount the sample, you can take a scribe, not a Sharpie marker, but a scribe, and you can etch the name into the side or the top of the sample that you're wishing to analyze. The reason why I say do not use a Sharpie marker is the fact that when you clean the samples between your polishing steps, which we'll discuss later in the grinding polishing process, the Sharpie marker will tend to come off. And then if you have 10, 15 samples, the last thing you want to do is mix those samples up. The risk of misinterpreting data or switching samples and mixing up data can really mess around with your research projects. So the types and the methods for casting, castable or cold mounting resins. You have vacuum impregnation, the hot compression mounting resins, and then conductive mounting resins. For the castable mounting resins, these are typically techniques that are used for materials that are heat sensitive. So low melting temperature metals and alloys, anything delicate that may collapse under pressure, or deform, or maybe the samples are just too large for any available mold size that you have for hot mounting, then your castable mount would be the way to go. So the least expensive and very quick method of, or I should say material, would be your acrylic resins. These typically cure within 5 to 8 minutes, and you're able to use the sample, after it cools down, probably 15-20 minutes afterwards. But that downside is the fact that it's hot enough to burn your hand. So with that being said, you're not going to be able to just handle it the moment it's fully cured. Cast epoxy resins, you have your two ingredients, one hardener, one resin. The way the epoxy resin works, the resin itself, long molecular chains, you add the hardener to it, and what it does, that hardener will start cross-linking those molecular chains and essentially setting up a thermoset. You do have a shelf life with these components, or I'm sorry, with these materials, so you can increase that shelf life to about a little longer by sticking them in the refrigerator, not freezing them, but just to keep them cool. Otherwise, you get a breakdown of the molecular chains, and then they won't bond well when you mix them later on. So the rule of thumb is, if you have an idea how much of this castable epoxy you're going to use, you would order based on a 6-month usage. If you don't use it a lot, then you do not need a 5-gallon drum of the resin and a 1-gallon bucket of the hardener. When you mix them together, you're going to do it by weight. So you'll measure them by weight instead of volume. And that gives you more of an accuracy to the ratio. Ratios change. Some call for a 10-to-1 mixture of resin to hardener. Some are 5-to-1, and some are 2-to-1. So it's going to depend on the brand and also the type of resin that you ordered. But when you stir them, you're going to stir it gently, kind of like mixing pancake batter. You're going to kind of fold it over one another. You're not going to mix it all fast. You're not going to beat it like eggs. So you're going to kind of just mix it around, folding it one over another for about 1.5 to 2 minutes, because you don't want to create enough agitation that'll form bubbles. The bubbles will then stay within your epoxy, and that just is grounds for another area for debris to collect around your sample, and so it just ends up being a mess towards the end. Cure times do vary when you're working with epoxy resins. So you're looking anywhere from an hour to 24 hours before you can actually pull the sample out and use it for the metallographic preparation. Your vacuum impregnation's nice, especially if you're dealing with components that are known to have maybe a lot of surface defects, voids, just anything that's going to cause an opening. So low viscosity epoxies are used, and they can be used to fill in the cracks, the voids, areas of corrosion, anything like that. When it's under vacuum, it helps just to kind of like push it in. And so what it does is, because now those voids are filled, it'll help you facilitate better sample preparation. With those cracks and all that stuff being filled, you have debris that will not collect, which will then pull out and push across your sample, scratching your sample. You reduce the risk of more bleed out of liquids, since you do use DI water, ethanol, and your etchants. So it helps in the long run. The better care you take for your sample after you section it, the reduce of any risk that you're going to mess up the sample towards the end. So when you're looking at hot compression, this is a very common method now that's used, and I use it 99% of the time. But it's a technique that utilizes temperature and pressure, and bakelite, phenolics, thermoplastics such as an acrylic resin, and you can even use conductive media. This technique is not ideal if you are working with pressure sensitive or temperature sensitive samples, just because the temperatures that you're typically looking at when you're hot mounting, and I'll use an example of what I've done that I do regularly. I'm typically operating anywhere between 95 to 100 psi, and the temperature of the media that I use is 200 Celsius. So low melting temperature materials where you're looking at 0.4, the melting temperature is that falls below that, then I would essentially be hot working and or annealing my sample if they were low melting temperature materials. So that's not good. Since I'm already altering the microstructure, I will not be able to correctly identify the true structure of that component. The phenolics are the most widely used. They're available in powder form. They're very cheap, simple to, I think for a 1 pound container of this stuff, you're probably looking at 25, 30 bucks. You can get the mineral filled phenolics, which help with edge retention. As we talked about earlier, retaining those edges for critical analysis of whatever you have on that surface, that's important. The problem with the phenolics is that if you do not have them cured at the, if it's insufficient, the curing temperature and or time, what ends up happening, the acetone and or high temperature etchants can actually attack the mount, and now you have a bigger issue with your sample. With hot compression, mounting must be cooled under pressure, and that's just to help avoid any shrinkage gaps between the mounted sample, the mounting media itself, and the sample. If you happen to pull the sample out too early and let it air cool, then what ends up happening, since it didn't cool under pressure, shrinkage will kind of move away from your sample, opening up gaps, and once again, gaps collect debris, increase the amount of bleed out you have when working with etchants and or alcohols and stuff like that. Conductive mounts. This is very nice for anybody who are interested in doing SEM work with their mounted samples. I do encourage that you mount the sample using a conductive mount. You can use copper, carbon filled, and nickel and or nickel flake. The copper filled is the most expensive, as anybody could probably guess that, but it does have the best conductivity and edge retention properties. This is copper filled, so it is a metallic, and I believe they mix this with silicon, very fine silicon powders, which help with the edge retention to increase that hardness of the media that you're mounting your sample in. But for a lower cost alternative, you can always go with the carbon filled graphite. It has the conductivity, but the edge retention and the conductivity are not going to be as good as the copper filled, but it does get the job done. So, I mean, there's nothing wrong with using carbon filled conductive mounts. And just in case your sample was huge and you had to use a castable epoxy resin, then you can add nickel flake to that resin, and that would help with the conductivity. Once again, not as superior as the copper filled epoxy mounts. So how do you optimize when you mount? After sectioning, you're going to realize when you take that sample out, you're still going to have cutting fluids, everybody's fingerprints, anything like that on the sample. So the best way to optimize your mount is to thoroughly clean and dry that sample. And the reason why is it's going to help increase that bond between the substrate, and the substrate being your metal, your sample, and your mounting material. If you have oils and residues, then what ends up happening is you don't get a good bond. It's going to kind of repel whatever your mounting media is, creating larger shrinkage gaps. So with a nice clean, thoroughly clean and dry sample, you can then reduce the shrinkage gaps, therefore improving the whole process going through the metallographic steps. So when it comes to then, and then for cleaning process, typically after I cut something, I always ultrasonicate it, the sample, for no more than 30 seconds in ethanol. Okay, ethanol is much better. Do not use methanol. I use ethanol for everything. So it's really nice because you ultrasonicate it for 30 seconds. The sonicator will help kind of break up even any loose debris you might have on your sample from the cutting process. And then when you go to mount, you don't have anything that's prohibiting that media to be right up next to your sample to help improve your edge retention. So looking at sample orientation, that importance of identifying the orientation will maybe help others understand the history or manufacturing processes in which your components were made. Cast products are relatively similar in all three orientation because it is a cast product. It will solidify the same in all three directions. So with that being said, you'll have similar mechanical properties in all three of those orientations. But wrought products, on the other hand, will experience anisotropy, and I know I touched on this in the last lab, but since your mechanical properties are going to be different in all three orientations, your microstructure will also look different in all three of those orientations. So to kind of give you an example, this is example one. This is a shaft, and I'm going to draw over my pictures here. But in order for me to get from this point here, and since everything's in blue, I'll use orange and blue, UTEP. So the main concern with this guy was the fact that they have a lot of failures in this region. And they gave me a brand new part. It's a 1045 steel. And based on what we talked about with sample orientation, the axial orientation for this shaft is going to be this way, correct? So since the axial orientation is the length of that shaft, then in order for me to get this resulting mount, I need to cut it axially. So I'm going to end up making two cuts on this sample. My first cut I'll make in purple is I'm going to cut circumferentially, which means I'm cutting right through here. Then my next cut is right through the center. Now I don't go right through the center. I go maybe just before, because there is a coating on this shaft that I need to then identify here. So the importance of this mount, this would be an axially mounted component. Okay, if I were to have mounted this guy in the circumferential orientation, then my mount would be nothing but the diameter of that shaft. And that's not telling me anything. So it won't tell me thread roots. It will not tell me what the coating is like in the reduced area right here. It's not going to tell me anything else. So in this case, the axial orientation is the most important evaluation that we created for this particular client. Looking at example 2, we talked about turbine blades in the lab, and with a water jet, you saw that I cross-sectioned off a piece here, and then I cut off a piece of the leading edge and a piece of the trailing edge. Okay, so my leading edge is this guy. My trailing edge, we'll use a different color. Let's go with red. This is this guy. And the dovetail section is that last remaining piece here. Okay. So looking at the orientations, in order for me to get these pieces, I cut axially and then transverse. But in order for me to look at whether or not I've got cracking in this dovetail region, I mounted it in the axial orientation. Okay, so this is the axial orientation. These other two, since I have to evaluate the coating, especially around the tip of the leading edge and the tip of the trailing edge, I need to mount those in the transverse orientation. So I'm looking at this surface right here on both of these pieces. Because if I were to mount it in the other orientation this way, and I were to look at this surface, it will look like a rectangle. It will not give me what that coating is like at the very tip. So this one is in the transverse orientation as long as this as well, and then this one is in the axial orientation. Looking at the third example, these are exhaust valves, and they failed in service. You can tell by the bend that they will not work properly. All they wanted me to do in this instance here was to look at the inertial weld that is what joins the valve stem to the valve head. So that piece is what we see mounted over here. Okay, this is the valve head. The weld, you can see that after the sample has been etched, the weld head is unaffected by the etchant. It's still dark, which means the etchant did not work on that side, and I'll explain why momentarily. But then you have a very distinct line, and here's your base material, and I'm not sure if you can see, but there seems to be some linear indications that run in this direction, left to right. You kind of see some dark banded features. Okay, so for me to get that particular sample, I had to make two circumferential cuts, one in the valve head, one in the valve stem. Okay, then I followed through with an axial cut through the middle. Now, you can see that I have a dark line here. That is a chrome layer. Okay, so that means this entire piece of this valve stem is chrome plated. Okay, the chrome plating ends right at that weld interface. So why and how were these welded together? This is 4140 steel, and it is inertia welded to a 2112 stainless steel, which is 21 nickel, 12 chrome stainless steel. So that's why this portion of the material did not need a chromium coating. It's already going to be protected in the environment that it's in. But they wanted to look and see if there was any failures or any signs of failures within this weld zone. Looking at sample number 4, good old pipe sample here. We have a API 5L X42 pipe. The X42 is the yield strength of this pipe. So how do I get, and this is number 20 out of 20 samples that I had to do metallography for. So the reason why I wanted to show this particular example is the fact that I will change colors real quick. Let's go to green. So this is number 20. The metallographic mount for this guy is right here. This is number 19 and this is number 18. So there were 21 total hydro failures, and they all happened to fail right in the weld. Okay. So that weld, as you can see, it's split from here to here, right along that weld seam. And after doing the analysis over this whole piece, you find the area where the initiation occurred, and that's what you document in your metallographic mount. Okay, so what would these, what would the orientation of these be? So we're going to, in order to intersect an axial weld, so this is in the axial orientation, so that's axial longitudinal weld, we're going to have to cut circumferentially our samples. So these are circumferential cuts because this is your long weld, your longitudinal weld. So this is a circumferential mount. Looking at the last one, I included this particular one here also just because, like the last mount, I was able to mount more than one. The difference between the last one and this is the fact that I have 4 metallographic samples in a much larger mount than what I had for hot mounting. This was done through vacuum impregnation, and based on the curvature that you see off of, actually the failure was right over here. This little collar, they have a hole, and it was leaking wastewater. So this is an ASTM A106 grade B pipe, and when you're looking at, this was obviously a corrosion issue, but when you're looking at corrosion, you're going to take more than just one sample. And what you're trying to do is look at the different pit morphologies when it comes to corrosion. So you can see that sample number 2, sample number 1, and this guy, sample number 4, are of circumferential orientation, okay, because you can see the curvature of the pipe more readily than the last one. The last one, I believe those were 20-inch diameter lines. This is only a 4-inch, I think it's 4-inch diameter. So you can see the curvature. So that means 1, 2, and this bottom one here, number, I'll just arbitrarily call it number 4, are circumferential mounts. Then the last mount has a girth weld, and a girth weld is applied circumferentially. So in order for me to look at a circumferential weld, I have to mount it in the axial orientation, which means this is one pipe, and this was another pipe. And this is the weld here. So this joined two pipes together versus the last image here, where this is the same pipe that's been welded together, and it failed on its own weld. Okay, so that would be another example of mounting a material, multiple samples in one mount, which helps reduce cost. It's ASTM A106, it's soft pipe. This is easy to polish and get your necessary analysis performed. So after those 5 examples, what we'll do in the lab is I will kind of do the demonstrations, show everybody how these are mixed, how to run a hot mount. Yes, you will still have the opportunity to do the equipment training and stuff like that. This is just kind of like a heads up of what to expect when you go in and actually run the equipment for yourself. So just some highlights. If you haven't already, sign up and complete that EH&S Lab Safety course. Write up your weekly summary. Those are due at midnight on Sunday. Same with the week 3 quiz. So I will be working on that quiz and getting it posted here in the next day or so. And then we'll meet on Friday for lab at 1:30. And it'll be just kind of like the last lab. It shouldn't take longer than an hour to kind of go over any questions you may have and to show the demonstration on creating some of these mounts. So please go ahead and complete the assignments, and I look forward to seeing everybody on Friday for lab. If you have any questions, please feel free to shoot me an email. Thank you very much for your time. Enjoy your week, and stay safe and healthy.